Salut. Okay, apparently it's time to restart, so let's go slowly. Okay, so what we did last at the end of last time was to use the bosonization formula to try to deal with spins. And that's where the thing starts to be really interesting. So we took, just as an example, the SXZ model, which is the model where I have the same coupling for Jx and Jy, which I call Jxy. Of course, there are parentheses here. And, yeah, for some... Okay. And I have a different coupling for Jz, which initially I will set to 0. We'll put it back later. And as I remind you, of course, these are spin 1/2. And spin 1/2 we showed can be mapped onto hardcore bosons. And so we can use everything we knew on bosonizing the bosons, even in the hardcore limit, which is the magic, because normally it should be a very complicated problem because of the very large repulsion between the bosons. But using the field theory, it's not really a problem to deal with that. Just as a reminder, I let you do it as an exercise. If I look at the ratio Jz over Jxy, the point Jz equals 0 is called, of course, the XX model. I mean, this is the model where there are only correlation when the spin is in plane. So you can expect the system to be dominated by in-plane correlations. Of course, it doesn't mean that the SZ component is not correlated, but there is nothing in the Hamiltonian, if Jz is equal to 0, that worry about what what SZ is doing. And then I have, of course, another magic point, which is the point where the ratio Jz over Jxy is equal to 1. And that's the Eisenberg point. This is the isotropic point where the system is invariant by spin rotation. So I have a question or an exercise for you. Is there a magic physics that corresponds to the ratio Jz over Jxy equal -1? It's a weird model, huh? You see, it's a model where you have here a positive coefficient, so it's antiferromagnetic-like for x and y. But if I say Jz equal -1, it would be like a ferromagnetic interaction for the Sz term. So is it a model you know or not? Yes? Yes. So indeed, if I tell it like that, it sounds like a model which I don't really know. But I can do a transformation where I will change Sx into Sx tilde -1 to the j. I will do Sy is changed into Ss tilde -1 to the power j. And of course, you could imagine I do the same thing for Sz, but if you do this, you violate the commutation relation, because the commutator of Sx and Sy is essentially Sz. So if I put a minus sign in Sx and Sy, I shouldn't touch Sz. So if I do this, I will do the transformation where Szj is Sg tilde j. And then when you do this transformation, of course, this term is not changed. And this term takes a factor -1 to the j times -1 to the j plus 1. So it takes a minus sign. So when Jz is equal to -1, this is actually exactly the physics of the isotropic ferromagnetic point. I could have put a minus sign in front of the three component, and I would have gotten exactly the same result. So this is isotropic ferro. This is isotropic antiferro, and this is a place where you're more dominated by in-plane fluctuations. And we discuss what happens here. When Jz is super large, it's more like an Ising model where you get only the coupling Sz, and we'll come back to that. Okay, so we worked out the bosonized theory. We worked out first the operators, the spin operators, and this is the representation of the spin operators. You see that this object has a very simple interpretation, at least if I am a little bit not too picky about it, for the antiferromagnetic component. For the antiferromagnetic component, Sz is cosine 2 phi, and essentially S plus and S minus are exponential of I theta. So you could roughly interpret physically the phi and the theta by saying that they are the angles that the spin is doing. So if I put a spin in a certain direction like this, you could say that 2 phi is essentially the angle compared to the z-axis, and that the theta angle is essentially the angle that controls the projection of the spin in the xy plane. And you have a very natural interpretation on the fact that, of course, these two fields do not commute, which is the fact that for spin 1/2, which is a quantum spin, you cannot determine the three components of this spin with infinite accuracy in the three directions. And this is telling you that, of course, you cannot fix as numbers the variable phi and the variable theta because they are canonically conjugate. So if you know very well the angle phi, it means essentially your spin is anywhere around in the plane. And on the contrary, if you fix very well the angle theta, it means your spin is fluctuating a lot vertically, so which is what you would expect for spin 1/2. Okay. Now, we did the calculation of the correlation in general, assuming we have a quadratic Hamiltonian with new velocity and new k. And we found these correlation functions here, which were that there is an antiferromagnetic part which is decaying for S plus S minus with exponent 1/2k, an antiferromagnetic part for Sz which is decaying with exponent 2k, and a ferromagnetic part in both cases. And we said if Jz is equal to 0, well, this is k equal 1. This is what we said before for the Tonks limit. And then we have this decay. Note, by the way, that the Sz correlation function is decaying as 1/x squared in that case, while the S plus S minus is only decaying for the antiferromagnetic part as 1/square root of x. And that's also, you're very happy because your Hamiltonian contain terms coupling the xy components. So you would expect this part to decay much more slowly than anything which is concerning Sz. So all is consistent so far. Okay. And then we try to bosonize the Jz term. And we found that there is two terms that are generated. One term that we love because it goes in the quadratic part, and one term which is a little bit more nasty because it's a cosine. So the term which is going in the quadratic part actually will provide you a change of the value of k. So here are my new equations. So you see that I will have k prime, which is square root, if I do the ratio, of something like 1 divided by 1 plus Jz over pi square times u. And it means that when Jz is increasing, k is decreasing. So in a way, I go to smaller value of k compared to 1. But probably, just like we did for the bosons, I cannot push this formula to absurdly large value of Jz, because, okay, I would go to k prime equals 0 again, and probably I have an accident before, just like for bosons, I said k is 1/square root of u, but we know it's not true, because for u equal infinity, k tends to 1. Okay? So we have to find the right value, and whatever. And we have to worry about this term here, which is a cosine, and of course makes the Hamiltonian non-quadratic anymore. But let me ignore the cosine by decree, by hand, and assume that I have just a quadratic Hamiltonian with a magic value of k. If I show you the correlation functions, could you, without calculation, give me the value of k for Jz equal Jxy, so the Eisenberg point? assuming it's quadratic, assuming the cosine doesn't play any role. I pretend I don't need to do a long calculation to tell you what is the only possible value of k if I have a quadratic Hamiltonian, purely quadratic, if my cosine doesn't play a role, at the Eisenberg point. At the Eisenberg point, the system is completely invariant by spin rotation. So, exactly, I heard it. So the correlation for S plus, S minus, which is Sx, Sx, or Sy, Sy, better be the same than the correlation for S, Sz. And they have different functional forms. So this is 2k, this is 1 over 2k. So if you want this correlation to match, the only possibility is k is equal 1/2. So you don't need to do calculation. If you don't find that, either your theory is more complicated because of the cosine or whatever, but it's definitely not quadratic. But if you assume it's quadratic and you put k equal 1/2, you see it works very well. This is 1, this is 1. This would be an exponent which is 1 plus 1, which is exactly the 2 that you have here. So it seems perfectly rosy, and most likely, at the end of the day, we will end up with a quadratic Hamiltonian with k of jz divided by jxy, which will be equal, so equal 1, which will be equal to 1/2. It immediately tells you that at the Eisenberg point, well, the correlation function, for example, Sz of r, Sz of 0, decays as minus 1 to the power r, 1 over r. And same thing, of course, for the other correlation, S plus, S minus. So correlation function in an Eisenberg Hamiltonian decay, or they oscillate, of course, they are antiferromagnetic, but the field theory tells you that they decay with a decay which is 1 over r. Actually, it's not totally correct what I'm saying. There is some part missing, but for the moment, I will ignore that. Okay. So you see that we have now a technology which we can use very easily to study spin problems. I am in the same situation than the bosons. I have the single spin operator which are expressed in terms of my field theory here, and I have potentially an Hamiltonian. Okay, there is this annoying cosine, but let's forget it for the moment. I will come back to the cosine later. I have an Hamiltonian, which is in principle the quadratic Hamiltonian, so I can compute any problem that I want. Okay, so let me give you one nice problem, if you want to do exercise. So problem 1. I take one spin chain. So H1 is J, okay, it's a XXZ model, I won't rewrite it, it's XXZ of the spin S1. I take another spin chain, so I will have H2, which is the XXZ model of the spin S2. And then, because I'm nasty, I will put a magnetic exchange, which will couple the spins here, which I will call J perp. So this is, let's say, J parallel. And I will put an extra term, so I want my total Hamiltonian to be H1 plus H2 plus J perp, and then on each side, sum over J of S1J scalar S2J. Question, what is the physics of this problem? This is called a ladder, of course, as you can imagine. And the question is, what is the physics of the corresponding problem? Well, the method is simple. If J perp is small, you write the field theory for chain 1, you write the field theory for chain 2, and you write the bosonized representation for the coupling term. And then you have a complicated Hamiltonian. Of course, it will not be quadratic, and it will have full many cosines, and you need to solve it. Okay? So that's a nice problem. I can give you another problem which is related. I take a chain of spins 1, and then I take an Hamiltonian, which is J, and the isotropic SI scalar Sj, and you solve it. Now you would tell me, but how do I do? Well, you cheat. And the people who cheated first the person who cheated first is Alan Luther, who said if I have a spin 1, I can represent it as the sum of 2 spin 1 half. And of course, it's wrong, because 2 spin 1 half, the Hilbert space has dimension 4. Spin 1, Hilbert space has dimension 3. So there is one state which is not there, which is the singlet state, when the 2 spin 1 half. But a singlet would cut the chain, so it's a high energy state, and I don't care. So I will replace my genuine problem with spin 1 by a fake problem, which is J, sum over Ij, of S1 plus S2, scalar, on side J, S1 plus S2, on side J plus 1. And then you see that this problem of spin 1 is not dramatically different from the ladder. Actually, it's a ladder where you get S1, S1, so you get this coupling. Then you get S1, S2, so you would have a diagonal coupling. Then you get S2, S1, you have a diagonal coupling on the other direction. And then you get S2, S2, so you get this coupling. So it's another version of the ladder. And all these problems you can bosonize, you can write them in the bosonized representation. Whether you can solve after depends on your ability to solve this nasty cosine term that will appear in the Hamiltonian. Of course, if you solve this one, okay, now it's too late. But if you had solved this one 30 years ago, you would be in Stockholm, and this is what happened to Duncan Haldane. This is the Haldane gap. So, of course, the behavior of this guy will be super different from the behavior of a single chain. Okay? Let's solve problem 3. So I will solve problem 3, and problem 3 will be a ladder with J parallel, J perp, and I will put a magnetic field. So I have H1 plus H2 plus J perp sum over J S1 scalar S2, and then I will put a magnetic field which is the sum over J, and it's S1Z plus S2Z. So I put a global magnetic field to polarize my system. And the difference with problem 1 and problem 3 is the magnetic field, of course, but it's something I will do, which here I want to solve it in the opposite limit, where J perp is much, much larger than J parallel. So how would I do that? Well, I know a problem I can solve is the problem where J parallel is 0. So let's solve this problem. Then this is what I get. If J parallel is 0, I get a bunch of uncoupled dimers. Now, I hope that you can diagonalize a two-side problem, and you know all the eigenvalues and the eigenvectors of this. You can classify them. You get the triplet plus, which is up, up. You get the triplet 0, which is 1 over square root of 2, up, down, plus, down, up. You get the triplet minus, which is down, down. And all these states, they are at an energy which is J over 4. And then you get the singlet, which is 1 over square root of 2, up, up, minus, up, down, minus, down, up. And this is at an energy which is minus 3J over 4. So at the end of the day, the energy, the ground state is, of course, many, many times degenerate, because you get the energy of singlets on each side, and then you get a degenerate triplet plus 0 minus on each side. So if you don't have a magnetic field, that's it. Now if I put a magnetic field, what would happen for the problem with J parallel equals 0? Well, that's very simple. The magnetic field will not do anything on the singlet. The singlet has spin 0, so I don't care. So the singlet will stay same energy. Sorry, this is the energy. And the triplet will split. So the triplet 0 will not be affected. The triplet minus would go up in energy, and the triplet plus would go down. Okay? So far, so good. It's a nice exercise you can give on the bachelor in quantum mechanics. And if you ask to plot the magnetization of the ladder as a magnetization per site as a function of the magnetic field, well, the problem is very simple. As long as the ground state is the singlet, the magnetization is 0, and then you reach a critical field where the ground state becomes the triplet plus, and then the magnetization becomes 1 per rung. So this is for a rung. Okay, so you have a quantum phase transition. Okay, it's not too complicated quantum phase transition, where all the dimers just go triplet at the same time. But now you can have more fun by putting back the J parallel. And then you immediately see what happens. And if you want the precise calculation, I let you look at a paper which we wrote with Alexei Zvelik. It's PhysRev B, and it's around 2000. I'll put the precise reference. What happens if you have J parallel? Well, if you create a triplet on one rung, because of J parallel, the triplet can hop on the next rung and on the next rung. So instead of having the same energy level, it's like a particle moving on a lattice. So you will have a band of triplet plus. So this triplet plus, they will acquire a dispersion, which is now, and the others too, but the others I don't care. So this band will acquire dispersion, which is of the order of J parallel. And now you see what happens. I have a band, and if I look at the energy of the triplet plus, I have a momentum index. I have a dispersion which will be a cosine because it's particles which hop on the lattice. And then, well, if I increase my magnetic field, then at some point, this energy level will go beyond the singlet, and then I will start populating the band of triplet plus. So it's like populating a band. And if I raise my magnetic field, at some point, the band will be totally populated. So instead of the curve that I showed you here, I will have now a curve, which is, I will have a first magnetic field, HC1, where the first triplet will enter in the system. Then the magnetization will grow, and at some point, I've put one triplet on every rung, and that's it. I start from an empty band of triplet, and I end up with a filled band of triplet. Okay. If you want to do the calculation, it takes a little bit more energy, but it's not super complicated. So you see that now I have two quantum phase transition. I have one quantum phase transition where the first triplet is entering the system, and I have a second quantum phase transition when I have totally polarized my system. Now, this sounds like a very complicated problem, but actually you can do a super simple mapping, because you can say if J perp is very large compared to J parallel, you can safely ignore these states. They are very high in energy. So at the end here, you only care about two states per rung, the singlet and the triplet plus for a rung. So I have a rung, and the rung has a Hilbert space which is reduced to two states. Does it remind you something? It's a spin 1/2. So I can completely map my ladder problem onto a spin chain problem. And when you do this mapping, which takes, as I said, a little bit of work, but nothing fancy, you find that this problem maps exactly on a problem where you get J parallel, and then you get SXJ, SXJ plus 1. So these are not the original spins, of course, plus S tilde YJ, S tilde y j plus 1. And then miraculously, you have an anisotropy 1/2 between jz of this pseudo spin and the original, and this original system. So it's exactly mappable in the limit where j perp is super large compared to j parallel. It's mappable on a magic spin chain for which the anisotropy, the original system is perfectly isotropic. But this pseudo spin chain is anisotropic with a magic anisotropy 1/2 that you will get. And again, spin up, the pseudo spin up is the triplet, and the pseudo spin down is the singlet. But now it means that I can play the game of the Tomonaga-Lottinger liquid, because this, in principle, I should be able to compute the K, the U, blah, blah, blah. And therefore, I should be able to worry about what is the physics of this problem in the language of my field theory. Why doing such complicated things? Well, because some people are actually able to synthesize this kind of materials. So let me show you a little bit. I think it's interesting. So here is what I told you a little bit more precisely. You get these ladders. Actually, in the material, they might even be more than one, so there is also a coupling between the ladders, but let me ignore that for the moment. You put a magnetic field, you polarize, and then essentially every time you get a triplet, you can either view it as a spin-up, or you can view it as a boson. We know that there is mapping between bosons and spin-up. So I can also view this problem as bosons hopping between the rungs of this structure. So actually, it's a very nice problem if you want to study Bose-Einstein condensation. So if you want to study Bose-Einstein condensation in condensed matter without doing cold atoms, you take these ladders and you just put a magnetic field on it, and the magnetic field is like a chemical potential for these bosons. Okay? So it's a chemical potential you can put on the bulk of the material. You can have a 3D material and study it. So if you want to, here is the paper I was mentioning, and if you want to know more how to make the link between the honest Bose-Einstein condensation that occurred at cold atom and the one that occurs in this system of spins, you have a correspondence which can be done. There is a little review article we wrote with Christian Ruegg, who is an experimentalist working on neutron scattering experiments, and Oleg Chernyshov, a theorist in the US, on this problem. Now, let me show you a compound, because, okay, you could say it's nice, he's blah blah thing, but okay, here is a compound. This is a genuine compound. These sites, the blue sites here, are copper atoms. The copper atoms have a free spin 1/2 on it, and because of the nature of the material, this is an insulator. So this is an excellent realization of the Eisenberg ladder. All these atoms in between don't play a role. They just serve to mediate the exchange, the magnetic exchange between the two spin 1/2, which are here and here, or here and here. And you get one type of exchange here and one type of exchange there. Just to give you a number, this exchange is about 13 Kelvin. This exchange is about 3 Kelvin. So it's relatively weak exchange, which is good, because if you put numbers, 1 Kelvin is 1 Tesla. So if you had normal exchange in condensed matter, which is 600 Kelvin, you would need to apply a field of 600 Tesla to polarize your system, which is inhuman. Nobody knows how to do that. You would need to go to some neutron star somewhere, but it's a little bit difficult, so it's better to reduce the exchange. And now you just need a field of 10 Tesla, which is very easily obtainable in high field facility around the world. Now, the largest field you can reasonably obtain, let's say 100 Tesla, is already super big. So here is the structure of the material. So the material is 3D, but the coupling between the ladders is super weak. It's of the order of 50 millikelvin. So if you work at temperature of the order of 1 Kelvin, you don't care. Okay, so this is a material in which one can play with these theories. So I have the Hamiltonian, I know it very well, I know all its parameters, and now I can play the game I told you before. I have my Hamiltonian, I do numerics on it, I get the Luttinger parameters. Again, trust me, the cosine will not play any role. So let's forget the cosine. So I need to compute. So I compute thermodynamic quantities like the spin susceptibility. I compute the amplitudes and so on. Here is the curve. It doesn't matter. Just obtain from numerics, from the MRG, as a function of the magnetic field. So the red curve is the exact result that is obtained for the ladder from the numerics. So this is K. You see that K goes from 1. This is when the band of triplons is nearly empty. And when it's empty, it tends to 1. Then it decreases. Then it re-increases when the band is nearly full. And this is the velocity. The other curve here is the velocity, which quite normally goes to 0 when the band is nearly empty, because you're at the bottom of the band, or when the band is nearly full. And you can compute this parameter exactly, with an accuracy which is arbitrarily good from numerics, from the MRG. The green curve is actually using the mapping I showed you of the ladder onto a spin chain. This mapping is only valid when J perp is super large compared to J parallel. And in the compound, it's 1/3. It's 3. So I don't know if you consider 3 as super large or not, but if you say it's super large, so I do the mapping, the spin chain is solvable by Bethe-Ansatz. And then I can take the Bethe-Ansatz solution and get the Luttinger parameters. And these are the green curves. So you see, it works qualitatively, definitely, same thing. It works much better for the velocity, by the way, than the Luttinger parameter. But of course, if you want precise numbers, you have to solve the right microscopic model, because 1/3 is not 10 million, and the mapping onto the spin chain only reproduce qualitatively the physics that you would like to have. Okay, now we have the Luttinger parameters. I have U, I have K. I can compute the amplitudes of the correlations. I won't show it, but it's the same thing than we discussed. And now I can inject these calculations into correlation functions like something called the Nmr Relaxation Rate, which is essentially the spin-spin correlation, local spin-spin correlation. And if you use the field theory, this is what you will get. You will get that the relaxation time for the local spin-spin correlation is a power law of the temperature with the exponent which reflects the power law decay of the spin-spin correlation. This is the d gamma function. This is gamma of x, gamma of y divided by gamma of x plus y and so on. Okay. The point I want to make, the formula is not important, is that in this formula there is not a single adjustable parameter. These are the amplitudes. Okay? So you get this thing. If you know U, you know K, you know the temperature, of course, blah, blah, blah. You can compute this. And it's not something you could have done with the field theory alone. The field theory gives you the formula, but it doesn't tell you what is K, what is U. Okay? What are the amplitudes? Now you take this. Okay, forget TC. Let's forget. You can get also something. And here is the comparison between theory and experiment. The experiments were done by Martin Klansek, who was at the time in the group of Claude Berthier in Grenoble, who is now in Ljubljana, and with an NMR professional, let's say it that way. And here is the relaxation time. This is when the magnetization starts to be non-zero. This is the full saturation. So this is about 7 Tesla. This is about 13 Tesla. And the data points here are the data, the measured data. And the red curve is the theoretical calculation without any single adjustable parameter. So you see that this combination of exact solution, numerics or Bethe-Ansatz, here the Bethe-Ansatz doesn't work that good. It would give you the green line because, again, the ladder is not a spin chain. It's slightly different, but it works qualitatively. But once you know the exact Luttinger parameters, then you can reproduce the solution with an accuracy which is absolutely remarkable. So this is an example where one can give a rather complete solution of the problem by combining the various techniques in the way that I explained to you. So for example, here is another quantity which this material has a transition towards an ordered phase, and you can again get excellent agreement between the theory and the experiment. The red curve is extracted from the field theory with again the parameters computed, and so on and so forth. There are other things which are less obvious that I will not discuss here. You can even test very precisely the analytic form of the Tomonaga-Luttinger liquid correlations. This was done in the group of André Zeludev in Zurich, where essentially you measure the S plus, S minus correlation as a function of Q and omega by using neutron scattering technique. So it's another ladder. It's not the same compound than the one I showed you. This one is called DIMPI. So they take the spectrum they got from the neutrons, and then out of this, they extract the structure factor, so the intensity of the neutron, which is the Fourier transform of this correlation as a function of Q and omega, plotted in a scaling form, renormalized by a power law of the temperature, and it's plotted as a function of the ratio of the frequency divided by temperature. And the analytic prediction from Tomonaga-Luttinger liquid is the straight line, is the black line here, with again an exponent that you know, an exponent which is not an arbitrary parameter. And you see that the agreement, so here the amplitude is arbitrary, so there is an adjustable parameter, but you see that the agreement between the data and the theory is amazingly good. The only adjustable parameter is the total normalization of the curve, so you can shift this curve up and down, but that's the only thing you can do. You cannot change the shape. So just to show you that this works. And that's what I wanted to say. This is also an urban legend that I want to blast, and I'll blast it tomorrow, is that's it. We can all go home. That's finished. Everything works. Let's do something else. Of course, that's the part that works. But for one thing that works, you will see many problems for which we still don't have the answer. Okay? So let's go back to our questions. And one of the questions we still have is, what about the bloody cosine? Because so far you took me on faith that, okay, I threw away the cosine and I tell you I can do it and whatever. And that's a very important question that we will have to worry about. So let's do the cosine, and for that I will change chapters, and I was on chapter. That's the problem. I have to go back. So it was bosonization. So now it's time to leave and to do chapter 3 and to do sine-Gordon equation. Okay. So I would say problems. So one problem we noticed was the XXZ model. So the XXZ is mappable on this sum over dx, uk, whatever, pi square plus u over k grad phi square. And then I get minus jz, whatever, divided by some constant, which doesn't matter at that stage, times integral over dx cosine 4 phi. And I have to deal with this thing. It's not the only problem where the sine-Gordon appears. Actually, because the fields are exponential of variables phi and theta, it doesn't require big thinking to realize that when you will multiply s at site 1 by s at site 2 and blah, blah, blah everywhere, cosine will pop up all over the place because the nature of the field. I will give you another example. Let me take the Liebling-Lininger, which were the bosons in the continuum. So there I was happy. I had just my field theory. It's the same, the quadratic one. But now I put plus a periodic lattice. So I add a small perturbative potential here, which is of the form V of x equal V0 cosine Q, not phi, but Q times x. Now, if I do this, what will happen? Well, if I do this, I will have my IH let's say, quadratic. And then I will add a term which is sum over dx of v of x times rho of x. And now we can go again. This is v0 sum over dx cosine q times x times rho 0 minus 1 over pi grad phi plus rho 0 exponential of I 2 pi rho 0 x minus 2 phi plus blah, blah, blah. Okay, let's look a little bit at the various terms. Okay, this is a constant, I don't care. This is multiplying grad phi, which is a smooth field, by an oscillating field, by an oscillating term. So if q is sufficiently fast, let's say q is not very far from the period of the lattice spacing. This term goes away. What about this one? This one and this one. You see that there are two possibilities. By magic, we'll see what the magic means, q is equal to 2 pi rho 0. If q is equal to 2 pi rho 0, the oscillation go away. Okay? So if I am in the case where q is equal to 2 pi rho 0, then there are no oscillations. And I am left with a term which is v0 sum over dx of exponential of I 2 phi, so cosine 2 phi of x. If q is different, but not too different from 2 pi rho 0, actually the oscillation don't completely go away, but they could become much more long wavelengths. So I'm left with a term which is v0 sum over dx cosine 2 phi of x plus delta times x, where delta is essentially q minus 2 pi rho 0. Now you could say, okay, you're too worried. It oscillates, I remove this term. After all, it oscillates, and that's it. And I wouldn't disagree with you, but I just want to point out that if the thing is super long wavelengths, maybe I should be a little bit more careful, okay? Now, what is the condition q equal 2 pi rho 0? It just means that the period of the potential that I have added is exactly corresponding to putting one particle to the minima of the potential. Just work it out, it's very easy. If you move by A, you want QA equal 2 pi, and if A is rho 0 minus 1, that's exactly what you will get. So this condition corresponds to the commensurability condition of the filling of the bosons with the periodicity of the potential that I have added. So you see that there are two cases. Either I have one boson per site of the potential. Potential is small. Huh? It's not a Hubbard model or whatever. It's just a small perturbation. And then my Hamiltonian is the sine Gordon. Or essentially in first approximation, the filling is not one boson per site. And if I am not too picky, this term completely goes away. And I'm back to the Luttinger liquid. So it first tells you that you can expect different physics if you look in terms of the number of particles, let's say rho here. When you have one particle per site, you can expect a magic physics here. I don't know which one. So this would be the axis, let's say, of the interaction. You can expect physics here, which will be described by sine Gordon. And here you expect physics, which is the conventional one that we studied so far, which is the one of the Tomonaga-Luttinger liquid, which for bosons is actually essentially a superfluid. Yeah.
So, in cases where this cosine is relevant, you open a gap.
We'll come to that, yes.
How do you know that the whole construction still makes sense, basically? Because you're no longer...
I'll come to that in a moment. Okay? So it tells you that we need to study this problem because it will occur very nicely in this context. It occurs also in a slightly different way. So let me rewrite the thing in terms of an action. So the action is something like 1 over 2 pi times k. And then I'll write it in a strange way. I'll write it dx d tau. Normally I always use phi, but this time I will keep the variable theta. So remember that the momentum for phi is the gradient of theta. So this I will keep, but of course the grad phi is the time derivative of theta. So I will write something, and I do velocity. Let's do velocity equal 1, not to be polluted. So I have here d tau theta square plus dx theta square. And then let's say I have a term which is minus g sum over dx cosine 2 phi of x. It's not very, very informative, but I can kind of reinterpret this Hamiltonian in a very, simple way. I can say this Hamiltonian is the Hamiltonian of a 2D classical model. It's the Hamiltonian of a 2D classical model where space is one dimension and tau, I can call it y, is the second dimension. It's an Hamiltonian where on each side I have only a phase, theta, an angle, theta, and I know a model like this. It's called the XY model, the 2D XY model. So if I take the 2D XY classical model, it's a model where on each side you put spins, which are described by an angle theta, and then the Hamiltonian is minus j sum on nearest neighbor of cosine theta I minus theta j. And if you're making an expansion of the cosine, if you say the thetas are not varying too much from one side to the next, well, this is roughly sum over dx dy of grad x theta square plus grad y theta square. It's called the spin wave approximation. So I can say, well, this part and this part, this is the same. So my quadratic part is like the part of my XY model that correspond to making an extension around the smooth configuration of the field. Now we also know, since Kosterlitz and Thouless, that you have to worry about vortices. And you have to worry about configurations where the spins would not be smooth configurations, but where you would have something where the spins can point out. So this is a vortex. By the way, this is also a vortex. Because if you want an anti-vortex, you need the spin to rotate in the opposite direction. So here the spin rotate like this, but here they also rotate like this, and it's only there that I've made my spin rotate in the opposite direction. So this is an anti-vortex. And you know that to describe fully the 2D XY model, you have not only to have the spin waves, but you have to incorporate the vortex. And I pretend, we still have 5 minutes, so we can even do it there. I pretend that this operator here is exactly the operator that will create a vortex in a configuration of the theta. Not totally obvious. Huh? So why is that so? Okay, let's try to do it. You remember your quantum mechanics? If I have a configuration X, and I want to translate it and obtain X plus A, what should I do? Yes, so you apply exponential of IAP to X, and this is essentially X plus A. Okay? So exponential of the momentum is the translation operator. So if I start with a configuration with a theta, where theta is fixed, and I apply something which is exponential A, I will translate theta. If now I apply exponential of I, A, integral from minus infinity to x on dx prime pi theta at point x prime and time tau, and I apply this on a configuration of the theta, what will I produce? I will produce something where on all this cut here, I will have made, so this is tau, this is x. On all this, I will have translated theta. So here I get theta, here I get theta plus a. Now the question is, what is the momentum conjugate to theta? Well, momentum conjugate to theta, from what we discussed, is 1 over pi grad phi. The same way that the momentum conjugate for phi is 1 over pi grad theta. So here, I get 1 over pi grad phi. Okay? So, if I apply the operator exponential of a over pi, integral from minus infinity to x, dx prime, grad phi, this is the translation operator, but this is nothing but exponential of a over pi, phi at point x, and time tau, times a non-important phase, which is the value of the field at minus infinity, which I can always fix to 0 or whatever I like. So this is my translation operator. Now, if I put, sorry, I said something wrong. It's not 1 over pi grad phi, it's pi grad phi. So here. No, that's correct, sorry. I'm mixing myself in the coefficient. It's 1 over pi, and I leave my 1 over pi. Okay, now I want to translate theta by 2 pi. So I want a equal 2 pi, and you see it's the operator exponential of I 2 phi. Now, of course, you will tell me, well, that's not a vortex, because then I go from 0 here to 2 pi. But now you can unfold the thing to make it more regular or whatever. It's the same topological configuration. So there is a one-to-one correspondence between the sine-Gordon theory and the creation of vortices, let's say, and the Coulomb gas, let's say, or the 2D XY model. And this was worked out by various people in the 70s, and that's something you can exploit. So now you can expect that this model, the sine-Gordon model, will have the equivalent of the Berezinski-Kosterlitz-Thouless phase transition. And that's something we will analyze after the break. I think it's a good point to stop here. But it immediately tells you that depending on the temperature of the classical model. What is the temperature of the classical model? Well, that's easy. It's that. If I take my Hamiltonian here and I put beta in front of it, it's like putting 1 over 2k in the action. So the temperature of the classical model maps onto 1 over k for the quantum model. So depending on the value of k, I will expect to have a phase where the vortices will be relevant, so I have to worry about the cosine. I cannot throw it away. And a phase where the vortices are irrelevant, and then I can throw away the cosine, and I'm back to my favorite quadratic Hamiltonian. And the precise value of k we will analyze in a moment, and that's exactly the Berezinski-Kosterlitz-Thouless phase transition. So I assume that all of you are reasonably familiar with BKT or not? Many of you are familiar with BKT? Okay, so, or not. Okay, so after the break, we'll detail BKT in much more detail. So I will not give you the classical version of BKT. I will give you the quantum one. But that's exactly the same. If you understand sine-Gordon, now you can read the paper by Kosterlitz and Thouless without any problems. So, okay, let's do whatever X minute breaks and 5 minutes. Okay. Yeah. No. Okay, yeah, sorry, I won't be there this afternoon because I have an appointment in another institute in Florence, but I will be there on Friday, of course, if you have questions, so don't hesitate to ask them, for those of you who are still there on Friday. Okay, so let's now try to solve so let's forget that it's connected to BKT, we live in the quantum world, and how do we solve an action, which is, again, 1 over 2 pi k, sum over dx d tau, and then this is essentially d tau. So I can write it in terms of theta, but I can also go back in terms of phi, as I did before. It doesn't matter. And then I have minus g, integral over dx d tau, cosine. Let's take p phi. Because you see that in one case I got a 2 phi, in the other case I got a 4 phi. Well, so let's be general and put p. By the way, a priori, it's not a big deal to change the coefficient in the cosine. Because if I can always introduce a field phi tilde, which I call p phi. But there is a price to pay. If I change the coefficient, it's just a change of variable. But if I do this, I also change k. Because I have to put p here, and phi is phi tilde over p, so I multiply k by p squared. So the price, I can change the coefficient in the cosine at will, provided I change k in the corresponding way. Okay? So just as a remark. Okay, so how do I study this? The first thing is to say, well, I will study it by perturbation theory. So if I do perturbation theory, I will expand my action, and then I will get that, if I do the expansion, I will get the integral over all the field phi of exponential of minus S0, and then I would get minus g integral over dx d tau, cosine p phi, blah, 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 plus g squared over 2, dr1, dr2. So this is what I call r here is dx d tau. And then I get cosine p phi at r1, cosine p phi at r2, and so on and so forth. The first term is relatively easy to see. Well, the first term is 1, but the second term, it's trivial to see that it's 0. We already discussed this term. It's the average of exponential of I phi, and it's exponential of minus infinity. It goes away. If you don't trust me, say that this configuration is completely invariant if you change phi by a constant, which would be pi over p, and because they have the same action. So for each configuration where phi is phi, I have a configuration where phi is phi plus pi over p. But it gives me a minus sign in this sum, and therefore it goes away. Sorry, which one? Well, this is functional integral, so everything is number. Everything is number. So everything is time ordered initially, then I map it on the functional integral. So at that stage, I'm dealing with numbers. If you want to do it in the Hamiltonian formalism, you have to be careful, but essentially I don't care. So I'm just saying this term is 0, so I don't care. The second term, I will have to look at something which is dr1, so d2r1 if you want, d2r2, and then the average of cosine p phi 1, cosine p phi 2, computed with the action S0. But that we know how to do. It's the quadratic problem. So this is exponential of minus p squared over 2 times k times log of r1 minus r2. So now you see that you have an integral, and you can look at the dimension of this integral. This integral, if you try to rescale it, it grows as a rescaling factor, which I will call L, to the power 4. So this has a dimension of L to the power 4. And then this is a power law, which is 1 over L to power P square K over 2. So this is L to power minus P square over 2 times K. So there are two possibilities. If the coefficient in front of the cosine is infinitesimal, I just need to look at the scaling dimension of the operator. And if this scaling dimension is positive, it will blow in my face if I try to do perturbation theory. If the scaling dimension of the operator is negative, then essentially this operator will become more and more irrelevant at large distance, and I can safely ignore it. I can do perturbation, but I can safely ignore it. And the fixed point at large distance will be given by the action without this operator. So I can expect a transition, and I insist for G infinitesimal, when 4 is equal to P square K over 2, so it means K equal to 8 divided by P square. So if I take, for example, P equal to, this will happen when K is equal to 2. So if I am with a field, if I am with a theory as a function of K, where K is smaller than 2, then I have to worry about the cosine. If I am above K equal 2, then the cosine is irrelevant. Okay. Remember the Tomonaga-Luttinger liquid for the bosons? We said K goes from plus infinity to 1 in the Tonks limit, so I will cross this value. So if I put one boson with a small lattice, 1 particle per site, something weird will happen if I crank up the interaction when the Luttinger parameter has a value K equal 2. And I can reach this transition. It's not something which is out of reach for the Tonks system, because I would go down to K equal 1, which is my minimum value. Now, what happens? Well, cosine is present. If I am very naive, you have a cosine, you would say, okay, I have the cosine, it's there. Let me expand the cosine. So instead of having the quadratic theory, I could expect to have a theory which is now S equal, let me go sum over dq d omega. I would have omega square plus q square phi star q omega phi q omega. That would be my quadratic action. And then I would have a term here which is G sum over dx d tau of 1 minus p square blah, blah, blah. Sorry, there was a minus sign because I need to expand around the minimum, and the minimum will be 0 only if there is a minus sign. P square phi square divided by 2. So up to a constant term, this is G. Sum over dx d tau of phi square, I can again go to q and omega. So this is G p square over 2 phi star q omega phi q omega. So at the end of the day, what I get is a theory where I would get sum over dq d omega of omega square plus q square plus m square times phi star q omega phi q omega, where m square here would be proportional to g. So I go from a massless theory, a theory where the excitations have an energy which tends to 0 when omega goes to 0 and when q goes to 0, to a theory where this time I get a minimum value for the interactions, for the excitations, because of the presence of the cosine. In other words, the quadratic term can let phi meander wherever it wants, but the cosine wants phi to be locked into one of the minima of the cosine, and then you do just small oscillations around this minima. So you have two phases. You have a phase which is gapless. And as I said, in the language of bosons, this is essentially a superfluid. And then you have a phase which is massive, and you will get exactly 1 particle per site, because now phi becomes a classical field. It becomes a number, 0. Which means if I inject it in my density does not literally fluctuate in any dangerous way anymore. And this is what people here called, so this is massive, gapped, let's say. And in the language of bosons, I go from a phase where the little potential here is not very important. The particle fluctuate a lot. And this is my superfluid with all the connotation that I should give in 1D. This is Tomonaga-Luttinger liquid. And when I pass k equal 2, I get a phase where essentially I lock one boson in one of the minima of the potential. And this is what people call a Mott insulator. So this is something which is an insulator because I have a gap to create excitations. I cannot have my system move. And it has a name. It's called a Mott insulator. So there are two things we should do because, of course, what I did, which is expanding the cosine, it's criminal. I shouldn't do that. Why? Because the fluctuations of the field are infinite, so I'm just expanding, not worrying about infinities all over the place. So there are better ways to do it. And I will give you two ways. I won't do it because it would take simply too much time to do the calculation, but I can refer you to an appendix, for example, in my book where this is done in great details if you want to do it. But essentially, you can only expand the cosine safely if you have normal ordered it before. So I can write that the cosine of phi is essentially something like the exponential of, well, the average, let's say, of the cosine of phi in the vacuum times the normal ordered cosine, and then I can expand. But I don't like this procedure, so let me just, it's not that I don't like it, it works, but there is a better way of doing it. And I like this method, so I will give it the method I like. Let's say I want to approximate this action by the best quadratic action I can find. Okay? So what is the best quadratic action? So this would be sum over S trial would be sum over dq, d omega, and then a whole function, which I will call g minus 1 of q and omega, phi star q omega, phi q omega. And I want this to be the best approximant of the real action. And then there is a procedure, which you will find in Feynman's book on statistical physics, which is that you should minimize the free energy corresponding to your trial action plus the average of S trial, sorry, S real, the real action, minus S trial, and this computed with the action S trial. Because if it was statistical physics, you could show that this is always larger or equal to the true free energy of your problem. So by minimizing, you find the best quadratic action that approximates. It's a beautiful variational method. It works beautifully in statistical physics. It works beautifully for quantum problems if you can write an action. Feynman used it to solve the Polaron problem. He found an approximate solution of the Polaron problem by a mass connected to a spring. So it's a ridiculously simple solution, but you have to find the right spring constant and the right mass constant, and that's it. Here, we can take as variational parameters the whole function here. And then when you do this, you will get a self-consistent equation for the mass. And if you solve it, you will get a much better expression for the mass than the one I've given you. You could also do a serious job, and I won't do it, but I will give you the result. The serious job is to do a renormalization procedure. So how many of you are familiar with renormalization procedures? Okay. So in short, the renormalization procedure is the following. I start from a theory with a cutoff lambda, and parameters. So here I have K, I have G. And what interests me in this theory is the low energy physics of the theory. But it's complicated because I have to integrate over all the modes from low energy to high energy and whatever. So I will try to connect this theory to another theory with a lower cutoff, lambda prime, which is smaller than lambda. And of course, you do it infinitesimally usually. You eliminate very few degrees of freedom. And of course, this new theory, I will impose it has the same low energy physics than the first one. So I don't want to change the physics. So the physics is the same. So physics 1 equal physics 2. But of course, if I eliminate degree of freedom, there is no guarantee that I will get the same parameters in my theory. I might even have new interactions that appear. And the idea is to find this transformation. And you find it usually perturbatively. If you can find this transformation, then you can hope that by iterating the transformation, at some point your theory will simplify, or maybe a miracle will occur, or maybe you will end up on a model which is exactly solvable. And then you use the exact solution. Whatever. You hope that a miracle happens on the way. Okay? And if it's the case, then you have solved all the problems because they have the same physics. Okay? So here you can do it because you have a cutoff, you have an ultraviolet cutoff in your theory. So you will eliminate degrees of freedom. There are several methods to do this. I don't want to go into the technicalities of doing it. I will just give you the result. So if I parameterize my cutoff by saying I have a cutoff which I call lambda of L, so just a convenient parametrization. This is the initial cutoff, lambda 0, exponential of minus L. So you see when L grows, my cutoff, my ultraviolet cutoff goes smaller and smaller and smaller. So I concentrate more and more on the low energy degrees of freedom. So I will have a variable K of L, and I will have the coefficient of the cosine, which is G of L. And now when you work out the equations, what you will find is one first equation, which is dk dl is equal to minus G square of L. And a second equation, which is dg dl, is equal to, okay, let me do it just for the p equal to, so I just do it for p equal to, is 2 minus k of L, of course, times g of L. Okay, and these equations were established first in, of course, not that form, by Kosterlitz, by Mike Kosterlitz, in the famous paper where he solved the 2D XY model. So this you how the parameters of the theory evolve if you look at lower and lower and lower and lower energies. So let's look a little bit at the solution of these equations. So first you see that if G is infinitesimal, I can ignore the first equation. It's not there because G is 0. But you see that the derivative of G will depend on the sign of 2 minus K. So if I start with K smaller than 2, G will grow. Cosine becomes more and more important. On the contrary, if I am for K larger than 2, G decreases. So I will have a part of the flow that I can draw in the variables G and K. If I start here, I will go down. If I start here, I will go up. Okay? But you see that at the same time, I go left. Because if I started with a value of K, which is here, I also diminishes a little bit K. So here I would go down, but I would go left. Here I would go up, but I would go left also. Okay. So I let you plot these equations. It's relatively easy with Mathematica. And the flow is something like this. You have a separatrix here, in which the flow is going to the point G equals 0 and K equal 2. And the other lines are bended like this. So you get something like this. And here you will get trajectories which will go like that. Okay, there is also a trajectory which is leaving like that. And now you will tell me what happens here. And the honest answer is I don't know, because I established this equation perturbatively in powers of g. So when g becomes large, I don't know, because the term I didn't write, the g4, g6, g8, they can do a lot of things. So you have to stop somewhere here when g is of order 1, because you cannot trust the result of these equations when g becomes large. Okay? So this is exactly the physics we were discussing, that there are two regimes. If you're somewhere there, then the cosine is irrelevant. But you see it has an effect. It renormalizes the value of k. So I end up with a fixed point, or a fixed line of points, if you want. All this is a line of Tomonaga-Luttinger liquids with renormalized values of k. So it doesn't matter if I use the trick of computing k exactly, because all this will be taken into account when I compute k from the numerics or from the... But if I wanted to compute k from the quadratic theory plus the correction of the cosine, you see that if I start at this point, I end up with a smaller value of k, which is this one. So the long distance physics will be controlled by this value of k, not the initial value of k. Okay, so that's why it's usually difficult to extract these parameters k by a perturbative expansion or whatever, because all these irrelevant operators, so of course in this region you say the cosine is irrelevant, all these irrelevant operators, they give you shifts of the value of the quadratic theory. On the other hand, if I am here, well, it's the opposite. I scale and I go to large coupling and I get my massive theory. So I get here the theory which is kept. Does it work? So let's see. Try to show you. So I put on the slides a little bit of things on the sine-Gordon. Exactly what I told you in words. This is the competition. You can view it as the cosine would like the particle not to fluctuate too much. As I said, either the cosine wins. And this is connected to Berezinski-Kosterlitz-Thouless transition. So for the example where I have a coefficient 2, the critical value is k equal 2. If I add 4, it corresponds to another critical value of k, and so on and so forth. Okay. Forget string order parameter. We'll come back to this. This is exactly what I told you. This is the vortex operator. This is the predictions that you can make. Okay, maybe I'll pass this. It doesn't matter, because I think there is much more fun to look at. Here is an experiment that was done in the group of Hans Christoph Nagel in Innsbruck, where they took the Lieb-Lininger model, the real one, the one which they can realize with cold atoms, and they took a tube of bosons, and he added a very small lattice. Well, actually, he added an arbitrarily large lattice, which means it can be small or large, and he looked at whether the resulting phase was massless or massive. And the way he does that is by some spectroscopy technique that I don't want to discuss. And what is plotted here is the strength of the repulsion. So this is the inverse repulsion. So the repulsion becomes larger and larger and larger when you're here. So 0 here is the Tonks limit. It's the limit of infinite repulsion. And this vertical axis is the coefficient of the lattice, is the height of the lattice. So when the lattice is super large, and they have 1 particle per side. When the lattice is super large, you would say, okay, I have a Bose-Hubbard model because my boson can only move on a tight binding lattice, fine. But then you reduce the size of the lattice, and you see that there is still a transition between a superfluid phase and the Mott Insulator phase. So massless, massive, massless, massive. And then you notice that all this curve, they accumulate at a finite interaction when the lattice height is tending to 0. And here is a much more precise experiment And the theory was done in collaboration with also Laurent Sanchez-Palencia from Paris. This was done in the group of Giovanni Modugno, not far from here, close to the airport in the Lens laboratory in Florence. So this is the same device, but they had much more accuracy on the experiment. So again, this is the strength of the lattice. This is the inverse of the interaction. And this is the place where the transition occurs. And you notice that when the strength of the lattice tends to 0, not really 0, but becomes very small, these curves accumulate to a finite value of the interaction. Which means for all interactions which are larger than here, any small lattice will produce you a massive phase. Of course, the size of the gap is tending to 0 when the strength of the lattice goes to 0. But this is always massive. And this is in perfect agreement with the RG equation I showed you. And actually, because it's the Lieb-Lininger model, you know the precise value of K for this magic value of the interaction. And you can check it corresponds straight to K equal 2. So this is something that can be tested in experiment. The presence of this cosine is giving you very interesting phase, which are not described anymore by Tomonaga-Oettinger liquid, which this is the way the Tomonaga-Oettinger liquid grows massive and dies, like all of us, essentially, by turning into a Mott insulator. Okay? So these cosines, they will produce a lot of disturbance of the physics I told you, because every time they are present, they will fight the quadratic term. The quadratic term like the field to fluctuate. The cosine don't like the field to fluctuate. They like the field to be locked into the minima. And therefore, there will always be competition. So when there is one cosine, this is sine Gordon, we can work it out. If you get 25 different cosines, it becomes a little bit more unclear where the system is flowing. Okay? So this is something we'll talk about more tomorrow. Yes? That's a very good question. So why is it giving you the right critical value? Because at the transition, the perturbative theory is still essentially exact. On all this side, you can start from something, you renormalize to G equals 0. So of course, if I take these perturbative equations, they are not giving you the exact shape of the curves. But at the end, these curves on the right, they will always converge to 0 by definition. That's what I call the phase which is massless. So the last part of the curve is always described by these equations, not this part here. And so when I will hit at some point this separatrix, which might not be a straight line, which might be very complicated, it doesn't matter. I will always renormalize at the end to K equal 2. So this part I cannot give reliably, but I'm sure that there is a separatrix somewhere. But when I will be on the separatrix, I still renormalize to G equals 0, which means at some point this equation will step in. And that's also why on the other side it's so difficult, because there, indeed, I flow to infinity and I don't know what to do in a serious quantitative way. Okay. But that's very important. Indeed, this dimension, in terms of the effective K, is correct. Not the original K. So you see, in a way, when I show you the numerics here, not the numerics, oops, they would kill me. The experiment here, and I show you the experiment here, you could say this point is on the separatrix. That's the point where the strength of the coupling and the value of the interaction puts me right at the edge between the two. So this is the separatrix. And here, I'm not at all at the right value of the gamma. But this is because I have a finite V. And this is the initial value of the K. But if I look at the low energy physics, I will renormalize and arrive at that point. So if I look at the superfluid correlation function at large distance, they will be described by K equal 2. Not at short distance. Okay, so that's a very important point. Okay, so this is something which is very important. So you get a quantum phase transition. Oops. And you can describe it relatively quantitatively. Now, this quantum phase transition, it has a very interesting characteristics. So as I said, if I am in the massless phase, well, you recover essentially the Tomonaga-Oettinger liquid. Again, right at the transition, this is what we said, you get universal decay of the correlation functions because you can replace this by the Kc, which is 2. And now, what is the order in the massive phase? And there we are touching something which is beautiful in one dimension. Because you could say, okay, in the massive phase, the density is ordered. Yes, I get 1 particle per second. Boring. What I pretend is that the order is much, much more than that. Why? Because if I look at my action, the thing which is ordered is phi. Now, if you think about it, it's crazy. Why? Because I start with a term which is minus cosine, let's say 2 phi. Okay? And I have the other term which is whatever, d tau phi square plus dx phi square. So initially, my system has many minima in the cosine. 0, 2 pi, 4 pi, 6 pi. Which one should I choose? Well, they are all good. So initially, you could say I have a discrete symmetry which corresponds to the minima of the cosines. Now, I told you phi equals 0, I expand around phi equals 0, but I could have expanded around phi equal pi. This was the same, because of the 2 phi in the thing. Okay, let me even remove the 2 here, just to avoid carrying factors of 2. So which minimum should the field phi choose? 0, 2 pi, 4 pi, 6 pi? And in particular, what about computing the average of exponential of I phi over 2? Is it 0 or is it non-zero? You see, if I say I have a configuration where phi is 0, and I have a configuration where phi is equal to 2 pi, this configuration gives me opposite signs here. So if I sum over all the minima, I get 0 for this term. And this is what I get in the Tomonaga-Oettinger liquid. But in the massive phase, the system chooses one of the minima and then stays there. So this is a remarkable thing because you get a spontaneous symmetry breaking of the minima that the system will choose for the cosine. And you're allowed to break a discrete symmetry in d equal 1. The same reason why the Ising model is ordered in spatial dimension 2 is because the Ising model has a discrete symmetry. The XY model is not ordered in dimension 2 because it has a continuous symmetry. For quantum problems, time acts as an extra dimension, so I shift the dimensions by 1. I cannot break the continuous symmetry of the phase of the wave function or the continuous translation symmetry. So this is impossible, even at t equals 0. But if my symmetry becomes discrete because of the lattice potential, then I can break it. Not always, but I can break it, and in the massive phase, it's broken. Which means that not only cosine phi has an average, but any cosine q phi has now an average. So in particular, this thing is now non-zero, which again is non-trivial, because if you look at all these minima, and you were summing over all these minima, you would say, when I'm here, this is +1. When I'm here, it's -1. When I'm here, it's +1. When I'm here, it's -1, and so on and so forth. So this is really the phenomenon of spontaneous symmetry breaking. And if you want to prove it, it's not easy. I highly recommend a book which is called Raya-Raman, which has been written by Raya-Raman, which is called Solitons and Instantons, because you have to show that there is no finite energy action that can connect in the massive phase one of these minima with the next minima. Because if there were, then there would be tunneling between these minima, and then that's it. This average would be 0. Now you say, why do I care? It's true. Why do you care? You care because, look at this. This is a very weird order parameter. It's a weird order parameter because the density rho of x is ρ0 minus 1 over pi grad phi, which means what I've written here when I write exponential of I over 2 phi of x, which looks like a nice local field, is actually an integral of the density over all sites up to point x. So it's a string. So this is something which is exponential of I over 2, and there is a pi, which I should put here, integral from -infinity to x of dy, and this is grad phi, so this is rho of y. So actually what it tells you is that you will get string order parameters. You will get non-local order parameters that will exist in 1D, and in a way that's the rule and not the exception. So you can define, even in situations where you cannot find a local order parameter, and one very famous example is the Haldane phase, where all spin-spin correlation decay exponentially, there is no average, no nothing, but nevertheless you can define a magic order parameter which is non-local. If you take exponential of the sum of the spins, this object is ordered. And here for the Mott transition, you get a non-local order parameter which says that if I was able to get a photograph of my system and measure the density on each site and compute this object, there is one phase where this object is 0, there is one phase where this object is non-zero. So I insist on this because the idea of non-local order parameter, so string, order parameter, is super important, and it's also very special. Now, in condensed matter, because the probes are local, well, you can never measure those. So people have been condemned for a long time to either compute them but never measure them, or to measure them in simulations, numerical simulation, numerical calculations. But the peace of mind of the theorist is over, because cold atoms, again, not only they provide you with this, but they provide you with, that's exactly what I was saying, you can do this. And to do this, you should have a one-shot measurement of the density everywhere. Well, they can. Again, the group of Immanuel Bloch in Munich. Here is a photograph of a plane of atoms, which is here, shown in a... And when they take this photograph, okay, photograph for a quantum problem, you should complain. What it means, they projected the wave function on the eigenstates of the density. So the density is either 0 or 1 or 2 or 3 and so on. But when they do this, of course, they destroy the wave function. They have to reconstruct the system, restart and whatever. But they can give here the Ni on all the sites of the problem. So then if they want to compute exponential of I sum of the Ni, they just compute exponential of sum of the Ni. And they do the quantum average by repeating the experiment. Repeating 10,000 times, 1 million times the experiment. So these string order parameters can be measured. And that's really nice because, okay, I showed you a particularly simple example of a string order parameter. But for example, Haldane phase, fermionic systems, they all get their string order parameters. Okay? So this is, I wanted to insist a little bit on this, because this is, I think, something very, very special to 1D that exists. Okay. Yeah.
Basically the same question I asked before. I'm still a bit worried since we constructed the whole of the liquid with the argument that we are on this line of fixed points of the Now you're saying we're actually in a different part of the phase diagram where we flow away from that.
Yeah.
So all of these terms that we've been throwing away
Yeah.
from the Hamiltonian, how do we know that they're not relevant?
You don't.
Okay.
You don't. And you have to reevaluate for each problem what will happen, and that's why not all problems in 1D are not solved. Because there are a lot of problems for which you have to worry, indeed, about everything you threw away. So I will give you a problem. Okay, this one was in good part now solved, but at the couple of years ago it was a nasty problem. So let me give you as an exercise. It's a nasty exercise because you will not be able to do it. Take a problem. No, I mean, you can do it, but you have to find the full solution, not the way you to do it. Take a 1D chain of bosons, and you put one boson per site. Okay? But I put a repulsion U on the site, but I put also a nearest neighbor repulsion V between two different sites. Okay, so that's a straightforward extension of the Hubbard model of bosons that I just gave you. Now, if V is small, you would imagine I can bosonize. Okay, perfect. So I highly recommend you to try to bosonize this problem if V is large. And you will see that all the formula that I gave you give you nonsense. Because you know the answer is V is large. If V is large, you will put two bosons here, 0, two bosons here, 0, two bosons here, 0, two bosons here, because you want to avoid paying V. And it's much better to pay U. But then you have put two particles on the top of each other, which means you're really in one of the disaster case that I was mentioning. The field phi is not smooth and whatever. So what do you do? And so you have to sweat a little bit for that. So you're perfectly right. When the system becomes massive, you're in trouble. You're also in trouble if you have two cosines, one of phi and one of theta. Because if the phi cosine wins, theta fluctuate like crazy. But if the theta cosine wins, then the phi fluctuate like crazy. Or it can be worse. You could have cosine phi, cosine theta. What do you do? And we'll talk about some cases like this tomorrow. So, no, there are many cases where one has to be careful, but at least the Tomonaga-Oettinger liquid provides you a starting point. And if these perturbations are not too large, you at least can control where you start from. But you're perfectly right. Everything we took for granted now needs to be reevaluated. Okay, let me finish because I think I'm the only thing standing between you and lunch. I probably have 5 more minutes. No? Okay, then I won't do it, but I want to do the teaser, so I will take it. In addition to being non-local order parameters, and we'll do it tomorrow, I have topological excitations. And why do I have topological excitations? Because you see that because of cosines, I can classify my excitations. I told you, oh, the cosine is there. What can I do? Oh, very nice. I can put the field phi at 0 here. But I could have put it also at 2 pi. What happens if, for example, I have an excitation that does something like this? It can only do something like this, because otherwise it's not ending in one of the minima of the cosine, and it will cost an horrendous cost in the action. But it's not necessarily 0, 0. It can be 0, 2 pi, or it can be 0, 4 pi, or it can be 2 pi, 0. So you have a way to classify the nature of the excitations based on the boundary conditions that you have. And because in 1D you get only 2 points in the boundary conditions, this is putting a very stringent condition. So for spins, you have a cosine 4 phi. So I recommend you to determine what is the smallest excitation you can do, and tell me what is the delta SZ, which corresponds to this excitation. We'll do it tomorrow. Okay, we stop here. So tomorrow we finish with the topological excitation. I will talk about fractionalization of the excitations, and then tell you all the problems for which we don't know the solution. So this will be exercise until the next school or whatever, where you will give the talk and give the solution. Okay, let's stop here and go to lunch.